Hi viewers, welcome to LMS Solution. Today we are going to see about design and performance analysis of three-phase solar PV integrated UPQC. So UPQC is nothing but a unified power quality conditioner. How we can develop UPQC integrated with the solar PV system. In order to simulate this three-phase solar PV integrated UPQC, we have followed some reference paper. This is the paper we referred in order to simulate this three-phase solar PV integrated UPQC. First, you have to discuss about some general structure of that solar PV integrated with the UPQC. This is structure. So it consists of a grid and then along with the non-linear load. Here you can see that this is solar PV system is connected to the series compensator as well as a shunt compensator. The shunt compensator connected to the three-phase system via filter inductor, and also the series compensator connected to the this three-phase system in series manner by means of this series transformer. This system, that means the series compensation and shunt compensation, it won't be powered by means of this PV array. That series compensation, shunt compensation having two different control. And also, what's the use of this UPQC? And the UPQC going to be used for the mitigate the voltage sag and swell problem in the load cell. Whatever sag and swell will be created in the source side, but going to be mitigated in the load side. That means we need to maintain 1 per unit voltage in the load side always. So in order to mitigate that voltage sag and swell in that source side, you have to use series compensation. The series compensator going to be inject some voltage in order to mitigate that voltage sag and swell in the source side in order to maintain 1 per unit voltage at the load side. And then what's the use of that shunt compensator? The shunt compensator going to be inject some current in order to mitigate that reactive power problem, as well as, for example, any unbalanced load will be in the system. If unbalanced load created in the system, during that time what will be happen, the source current will be is non-sinusoidal. Because of non-linear, what happened to the source current? The nature of source current also going to be is non-sinusoidal. We need to make that source current to sinusoidal. For that, we have to use that shunt compensation. Shunt compensation going to be supply some reactive power current not to compensate that reactive power in this system. That's why it's going to be make that the input current sinusoid during nonlinear load condition as well as unbalanced load condition. The source current always sinusoidal because of this shunt compensation. Next, we got to see about circuit, that means control logic used for shunt compensator. This is the control logic used for shunt compensation. Here they are used MPPT algorithm. So MPPT will be receive PV voltage and current, and then it will generate reference DC voltage, and then you have to measure the dislink voltage from that system, and then it's going to be compared with here. After that, when we process via PA controller, so it will provide some current. So this is nothing but a I loss current. Next, you have to measure load current, and then it's going to be converted into DQ0 reference frame, ABCD to DQ0, and then you have to take only direct axis load current. Then it going to be used for here, and then based upon PV power and then grid terminal voltage, you have to find out the I power from the PV panel. Based upon these three current, IL, D, and the I loss and I average, you have to generate a reference current in the direct axis. So it will provide the controlled direct axis current. So next we need to convert this current ISQ and I naught going to be 0, and then based upon this three input we need to convert DQ naught into ABC, and then it's going to be processed by a hysteresis current controller to generate the pulse for that shunt compensator or shunt filter or shunt inverter. So this is a control logic for shunt compensation, and then next you have to discuss about the compensation for that series compensator. That means control logic for series compensator. Here we need to measure load voltage and then grid voltage. Next you have to convert ABC to DQ naught. Here also you have to convert ABC to DQ naught, and then you have to compare the direct and the quadratic axis voltage in both the voltage and the source voltage. And then next here you need to compare with some reference voltage. That means here you have to compare with the VLD reference and the VLQ reference with the source voltage or grid voltage. That means VST and VSQ. After that, you have to compare this signal with the here from this output of the summer, and then you have to process this signal via PA controller will generate that the control output in the form of VSCD and VSEQ. Next, it's going to be converted into ABC by means of PQ not to ABC transformation, and then it is going to be used as a controlled signal. This three-phase voltage going to be considered as a controlled signal for that PWM generator. So this is going to be processed via this PWM generator and generate the pulse for that series voltage source converter. Nothing but series compensator. This logic began is series compensation and shunt compensation. Next, you have to see the MATLAB simulation model of this solar PV integrated with the UPQC. Here you can see that the solar panel. Solar panel receive two inputs. One is irradiation, another one is temperature. And then here we are using that P&O algorithm. The P&O algorithm receive two inputs, voltage and current. Based upon the voltage current, you have to generate the reference voltage here. This is the reference voltage, and also here we are measuring that power from the solar PV system. This P&O algorithm will generate the reference voltage for the sun compensation control logic. Next, you have to see about the sun control logic here. Sun compensator control logic here. Here we are going to measure load current, and load current going to be converted into DQ naught, and then you will take only IL, the direct axis load current, and then here you have to measure the solar PV power and then divide with the terminal voltage of the grid. It will give IP average, IP generation, that means power generation, that means current based upon that PV power. This is nothing but IL, DF, and then based upon that P&O we have that reference voltage. This reference voltage is going to be combined with the actual DC voltage here in process via PA controller. So this will be provide loss current, I loss current, and then here we are summing that this three current. This is going to be known as IS and D star. So next you have to convert this ISD star to ABC by using DP naught to ABC, and then you have to compare with the current that means sun converter current, and then process via hysteresis controller. It will generate the pulse for that sun compensator. So it will generate three current. So we need to use not logic to generate the 6 pulse G1, G2, G3 and G4, G5, G6, and then this pulse going to be given to this sun to voltage source converter. Based upon this current from that PV panel and then load, and then here that DC link voltage, when we control this voltage source converter not to mitigate the problem because of this on load as well as unbalanced. Next you have to discuss about series compensation logic. Here you can see that we are going to measure load voltage and then going to be converted into ABC to DQ naught, and then here you need to measure the grid voltage. This is also going to be converted to the ABC DQ naught, and then you have to compare here first, that means the load voltage direct and quadratic axis voltage is compared with the source voltage. After you have to compare this source voltage with the reference voltage. After that the output of this sum going to be compared with the output of this summer, and then it will going to be processed via PA controller. It will generate two signal, nothing but the VSC and VSEQ, that going to be converted into ABC by means of DQ naught to ABC conversion, and then process via PWM generator. It will generate the pulse for that series voltage source converter. This pulse going to be given to here this voltage source converter. This series voltage converter is connected via this series transformer to the grid. Here this both sun to voltage source converter and the series voltage source converter is connected to the solar PV system, is powered from that solar PV system. The series voltage source converter going to be inject the voltage based upon a condition of, that means exact swell condition of the grid side. So here we are created three conditions, one for voltage sag, another one for voltage swell, and another one for unbalanced load. So, and also we have connected non-linear load here. The TH level is around 22.24%. Here you can see that this is the voltage sag swell created in the system. From 0 to 3, the voltage magnitude is 1 per unit. From 3 to 3.5, the voltage magnitude is 0.8. And then 3.24, the voltage magnitude equal to 1. From 4 to 4.5, voltage magnitude equal to 1.2. After 5, the voltage magnitude equal to 1. This instant 3 to 3.5, you have to create voltage sag. From 4 to 4.5, we created voltage swell. During the time, the series compensator should inject some voltage to compensate this sag and swell in the load side. That means we need to maintain load voltage at 1 per unit. Next, we created another even nothing but the unbalanced load condition. The breaker will be connected in the C phase of this load. The breaker will be operated during the 1 second. From 0 to 1 second, 0 to 1 second will be closed. After 1 second, it will be opened in order to create that unbalanced condition here. So this breaker will be open up to 1.2 seconds. Up to 1.2 seconds. From 1 to 1.2 second, the load will be unbalanced. So during that time, we need to maintain sinusoidal source current. We need to maintain during non-linear load condition also. We need to make the source current is sinusoidal, as well as during unbalanced load condition. We need to make the source current sinusoidal. That means we need to maintain unity power factor logic in the source side. We have to create that unbalanced and non-linear load condition. We will create here. We are using this 3-phase rectifier with the RL load for non-linear load condition. And then here we are using that breaker to create unbalanced load condition. From 1 to 1.2 second, unbalanced load condition is created in the system. From 3 to 3.5, voltage sag is created. From 4 to 4.5, voltage swell is created. So next you have to check the response of the system. Here we measure different details. This is known as grid voltage and grid current. This one grid voltage and grid current. This is sun to voltage source converter voltage and current. And then this is known as load voltage and current. And this is grid voltage. This is load voltage. And then the voltage inject by means of a series voltage source converter. And then here you can see that. So this is irradiation temperature and then voltage across the PV panel and current from that PV panel. So this is power of the PV panel. Next I am going to explain about that events. So first I am going to explain about the unbalanced load condition. From 1 to 1.2, right? Unbalanced created in the system. That means loads are here. You can see that from 1 to 1.2, C phase will be disconnected from the system. Then the unbalanced condition will be created here. During unbalanced condition, you have to check the source current. Source current nature is sinusoidal. It's maintained sinusoidal source current. And also the remaining time you can check that the nature of input source current. Here also that will be sinusoidal to sinusoidal. Next I'm going to show you that the next event nothing but the swell event. Here that from 3 to 3.5 sag is created in the system. Here you can see that there is voltage sag is created here this point from 3 to 3.5. Because of the voltage is reduced to some level. But now during that time what happened to the voltage source converter inject some voltage in order to maintain 1 per unit voltage at the load side. Same way you can see that from 4 to 4.5 and the voltage swell is created here. The voltage will be increases to 1.2 per unit. During that time also the series voltage source converter inject some voltage in order to maintain 1 volt voltage at the load. For sag and swell condition, the load voltage maintained at 1 per unit because of that series voltage system. And also during because of nonlinear load and unbalanced load condition, the source current will be maintained at the sinusoidal. During that unbalanced load condition also, the source current is sinusoidal. For all even when unbalanced load condition, nonlinear load condition, voltage sag and voltage swell, the solar PV integrated with the UPQC system will be work fine. It will be mitigate the all products, sag, swell, unbalanced condition and non-linear load condition. Thank you for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much.